Chapter 10, verification and validation, the last part of videos, part 3. As we saw in the previous part, in part 2, in our example, we run the simulation model for n replications. So we have a sample data with size n, and then we can apply a hypothesis test to see if the results obtained by the simulation model are consistent with the results obtained by the real system. Okay, we can do another thing here. Instead of having a hypothesis test, we can obtain a confidence interval. So a confidence interval for our parameter, which is here average delay or waiting time, so can be obtained by this. So the y bar is the sample mean, s is the sample standard deviation, and n is the sample size, and the t half alpha n minus 1 is the critical value obtained by the t distribution. So we can obtain a confidence interval for that average delay by this equation. And then if the population mean falls in this interval, I mean in the confidence interval, then we fail to reject the null hypothesis, or here we say that since we don't have hypothesis test, so we say that yes, the sample data is consistent with the real data. And if not, actually we say that the simulation model is not behaving like the real system. Okay. So as you know, the simulation model works with generating artificial data, right? We do have the statistical distributions for the model's parameters, and then the simulation model generates random numbers, random variates, and then goes on to the process by those random numbers and variates. Okay, so yeah, like what we have done so far in the previous example in part 2, that was our approach. So we run the simulation model for several replications. So we do have a sample data by having the results of replications, and then we run a statistical method to see if the simulation model is behaving like the real system. It could be a hypothesis test or a confidence interval approach. So here we do have another approach, which is called using historical input data. So it's an alternative to generating input data. This means that we block that part in the simulation model that generates random numbers and random variates, and we feed the data, I mean for interval time, for service times, we feed the actual data. So we have historical data from our real system, and we feed the exact numbers, the exact values for interval time and for the service time. And then we'll see what's the output of this simulation model. So here, since we're feeding the exact numbers, I mean the exact values of interval time and service times from the actual system by having the historical data, so we expect to have somehow same results, right? Same output obtained by the simulation model in comparison with the real system, right? So this is called the validation using historical input data. So here we compare the response from a simulation model and the real system with the historical input data using a hypothesis test. So here we do have input data. Let's show this by J. So J goes from 1 to K. So we have K input data. Okay, and the system output Zij, I here is for a performance measure, right? A performance measure. Let's say we do have several performance measures like waiting time, the number of customers in the system, and so on. So I here is for the ith performance measure. Okay, so the Zij, Zi1 up to Zik are the real outputs in the real system that we do have in our historical data. And the Wij is the response obtained by the simulation model, Wij, for those k input data. Okay, so the observed difference, so here we calculate the difference between the model's output and the system's output for each given data. Okay, so yeah, D1 becomes ZI1 minus WI1 up to dk here. Okay, now we do have the difference, observed differences. So the D bar will be the average difference. The S can be calculated here as the sample variance. Now we can run a hypothesis test here. H0 mu D equals 0 and H1 mu D not equals 0. Okay, so yeah, it's exactly the same as before. We do have the t-test analysis here. The t0, the statistic can be calculated by this t0 d bar minus mu d divided by sd over square root of k, and the degrees of freedom is k minus 1. So again, if the absolute value of t0 is greater than t half alpha k minus 1, the critical value, we reject the h0. Other than that, we fail to reject the h0. Okay, let's have an example here, the candy factory. So the production level of candy factory was recorded for 5 days. So we do have data for 5 days, and our performance measure is production level. So with all input data, so yeah, the input data were later used to simulate the production level, and now we want to validate the simulation model against the real system. Okay, so yeah, here we do have 5 data for 5 days, so input data will be from J1 to 5. So we do have the system production level, so that's the system's outcome or output. So we do have the numbers here, and also the production level obtained by the simulation model, Wij. So we can calculate the difference between the system's performance and the model's performance. Okay, now by having the differences, we can apply a hypothesis test here. So alpha is 5%, k, the sample size here is 5. So the d bar, the average by these numbers, okay, becomes 5,343.2, and the standard deviation for the sample data is here as well. So the t0 is calculated and the value becomes 1.37. And now we go for the t distribution table in order to obtain the critical value. Since alpha is 5%, the half alpha becomes 0.025, and the degrees of freedom here is 4, k minus 1, right? So the critical value is obtained by the t distribution is 2.78, and as you see here, the 1.37 lies between the negative 2.78 and the positive 2.78. So we fail to reject the null hypothesis. Okay. The last method that we are going to learn in this chapter is a Turing test, and it can be used in addition to the statistical methods, or in case that we cannot apply a hypothesis test or confidence interval, then we can use the Turing test. So, and this method is based on the expert's opinion, the expert's investigation or judgment. Okay, so let's have an example here. Let's say we have 5 reports on the system performance. So we have 5 reports from the real system, and then we prepare 5 reports by running the simulation model. Let's call these 5 as fake reports. I mean, they're not fake, but they are fake since they are not from the real system. Okay, so we do have 5 real reports and 5 fake reports obtained by the simulation model. And then we will provide these 10 reports, we shuffle them, and all the format, structure, everything should be exactly the same, that experts cannot actually distinguish between the fake one and the real one by the face evaluation. Okay, so then we ask the experts to identify the fake reports from the real one. So if the experts identify the substantial number of fake reports, then the performance of the simulation model is questionable. I mean, the experts could identify the fake ones. So this means that the simulation model is not behaving like the real system, right? So by having this, the simulation model needs to be modified. But if not, I mean, if the experts cannot obtain the fake ones, or they obtain the less number of the fake ones, then we can conclude that the simulation model is working well. So, and that's it. So in this chapter, we learned that how we can verify and validate a built simulation model. Okay, thank you.